This is the fourth and final part of my introduction to eigenvalues and eigenvectors. I want to make clear this description of what we mean by the characteristic polynomial, since it'll be used quite often. We are dealing with finding eigenvalues. The characteristic polynomial will allow us to find the eigenvalues. And we're going to be working with 2 by 2 matrices, so when I write capital A, I'm referring to some generic 2 by 2 matrix ABCD. And I'm also going to need to make use of a 2 by 2 identity matrix 1, 0, 0, 1. And the identity matrix has the property that anything times the identity matrix doesn't change, just as the number 1 is the identity element. I times A is still just A. The equation that we use to define what we mean by eigenvalues and eigenvectors is this one, that A times xy, if xy is an eigenvector, then after being multiplied by A, we just end up with something in the same direction as xy, but stretched by an amount lambda. We're going to set up an equation that called the characteristic polynomial that lambda has to satisfy, that will allow us to find values of lambda, and it requires just a little bit of manipulation. I'm going to bring the lambda term to the other side, and so it'll look like this: A times xy minus lambda times xy. And I want to factor out the common xy from each of these terms. However, that would leave behind a matrix and a scalar, and that's not going to work for us. And so what is done is that we introduce the identity matrix, A times xy here, minus lambda times I times xy. That's essentially multiplying by 1. Nothing has changed. And now I can say this is A minus lambda I times xy, and that's A, B, C, and D, and lambda times I is just lambda 0, 0, lambda, all times xy, and that's 0. And then putting it together, I have that that's A minus lambda, B, C, and D minus lambda. And this is a similar situation we've found ourselves in before, where we're looking for a solution of this homogeneous problem where the right-hand side is 0. Of course, xy being 0, 0 will make this true, and that's called the trivial solution. But non-trivial solutions will require that, that this determinant of this matrix is 0. So I'm just going to write that non-trivial solutions require that the determinant which would be called, in this case, the coefficient, determinant of the coefficients, A minus lambda, B, C, and D minus lambda, that the determinant matrix B0, and when we compute this determinant, I'm sorry, that is a lambda, I get A minus lambda, D minus lambda, minus BC, and that has to be a 0. This will always lead us to a quadratic equation. In this case, it's the equation lambda squared, plus I have an a plus d lambda term, and then I have a cross term of AD minus BC, and this has to be equal to 0. And this equation is what we refer to as the characteristic equation or characteristic polynomial. And that's where I'll stop. Let me say one more thing. We also will refer to it sometimes as, you'll see this statement, the determinant of A minus lambda I as 0 also is sometimes, even though it's not in its polynomial form yet, is the characteristic equation. And these two things you'll see me write quite often, so I want you to be comfortable where they come from. Thank you.